All right, everybody, this is Mr. Ainsworth. We're going to get into volume review number 1, and we're going to take a look at how to set up and evaluate an integral to find the solid revolution about the y-axis. Okay, y-axis here. So we're going to be revolving this way. Okay, so this blue region right here is going to be revolved around the y-axis. Okay, and so it's going to be reflected over here. So we're going to need to draw that in a minute. We're going to do it two ways. All right, first using the disk method and then the shell method. And in the shell method, we're going to have to change the cross-section. Right now, this is set up for the disk. All right, so the first thing I'm going to do is I'm just going to reflect it over here. Okay, that's over here at -4, 4 units on the other side. No. Okay, and so this blue region is reflected over here. And what's represented is here is a cross-section right here. Cross-section. And when you see it right here, it becomes a disk, because this is our disk. Its thickness is dy. It's a difference of two y values, so it's a differential in y, or dy. And because of that, we have to write an integral, okay, in respect to y. And our disks are going to go from low to high. Okay, they're going to be horizontal, starting down here at 0, going all the way up to 4. So we're going to integrate from 0 to 4. All right, but any integral involving y here has to be solved for x in terms of y. So what I need to do is take this equation and solve for x. That's the very first thing you need to do here. Well, you need to solve for x in terms of y when you write an integral in terms of y. Okay, so I square both sides and I get y squared is equal to 16 minus x squared. I add the x squared on the left and then I subtract the y squared to get it on the right. And I get x squared is equal to 16 minus y squared. And you simply root, and you get the square root of 16 minus y squared. To go any further than that, I've seen a lot of people square root the 16 and the y squared and try to simplify it. But that'd be an illegal algebraic move, so don't do it. Okay? All right, so that right there is x in terms of y. And what we need to do is use the disk method first, and that calls for me to find a of x, the cross-sectional area. Okay? And that's going to be equal to pi times the radius as a function of y now squared, pi r squared. Well, what's the radius? Well, it's going to be right here. Sorry about that. Okay, so what is the radius? Well, the radius is this distance right here. And at this point, it's some x value, so the radius is equal to x. Okay, but what is x in terms of y? Well, it's equal to the square root of 16 minus y squared. Okay, so your cross-sectional area here is found by, or the area of the disk here is pi times the radius squared. So what I need to do is take pi times the radius, which is 16 minus the square root of y, all right, and square that. That's pi times radius squared, and that's going to be equal to my volume, okay, of revolution if it's revolved around the y-axis. Okay, and you go ahead and do the arithmetic there. That's going to be pi times the interval from 0 to 4 of 16 minus y squared dy. Okay, you integrate pi times 16y minus y cubed divided by 3. Evaluate it from 0 to 4. Do the arithmetic there. It's pi times 16 times 4 minus 4 cubed divided by 3 minus pi times 16 times 0 minus 0 cubed divided by 3. Okay, all this second thing is equal to 0. And the end result when you simplify it is 128 pi thirds. All right, cubic units, and that's the volume. Okay, now that's if you use a disk and you're revolving around the y-axis with a horizontal cross-section with the thickness of dy here. If you're going to do the same thing and revolve it around the y-axis, but this time use a shell, you have to do a cross-section that's vertical, and that's perpendicular to the x-axis. So let's see why here. Let's go over here at -4. All right, and let's draw this thing in 3 dimensions. Okay. So to draw a shell and not a disk, you got to go have the cross-sections perpendicular. Let's reflect it over here, and let's draw a shell. Okay, you can see that. This is a shell now. And what we need to do is figure out its radius right here. that's r, and its height right here, h. Okay, and we have to write those as functions of x this time because you'll notice that our thickness is dx. Any cross-section that's vertical has a differential in thickness as dx, and any cross-section that's horizontal, like in this previous one, has a cross-section thickness of dy, because there's a difference of two y values. All right, so I need to write a shell volume in terms of x, okay, because its thickness is dx. I'm going to take a look at a shell volume first. Now the shell volume is the circumference 2 pi r times the height h times your thickness, in this case is dx. So I needed to find the radius and the height in terms of x. So let's go ahead and do that. Well, at this point right here, this distance right here is, let that be x. Okay, so the radius is equal to x. The height, okay, h, is going to be, some function of y, is a y value. It's vertical, okay? But what's that y equal to on the function? Well, it's given to be the square root of 16 minus x squared. So you can't say that the height is always constant, it's always 4. It depends on where the cross-section is made, and that changes from left to right from 0 to 4, which are the bounds, a equals 0 and b equals 4 here. So the height is 16 minus x squared. So you take 2 pi times the radius, x, times the height, which is the square root of 16 minus x squared, times your thickness, dx, and that's your shell volume. And to find the total volume, want to integrate from 0 to 4, because the cross-sections are vertical. So I could have drawn the cross-section here, or here, or here, or here, or here. So it's going to go from 0 to 4. Those are the bounds. So from 0 to 4 of 2 pi x times the square root of 16 minus x squared, all right, dx. Now this will give us the same result, and you should put it in the calculator and check it out. It'll give you a decimal result, but it's going to be the same thing as 128 pi thirds. So you can check that on the calculator, and I suggest you do that as you go through the exam. Get good at it. But you also want to be able to evaluate this. And so notice here that the derivative of this is sitting right out here on the outside. And so that means that we could use u substitution. So 16 minus x squared will equal to u. My du would be equal to negative 2x dx right here. And notice I almost have it out here. So what I'm going to do is I'm going to just divide by a negative here. So negative du equals 2x dx. So here's that part right there. That's negative du. I'm going to bring out the pi in a minute. I take out the pi right here. I can take out the 2 if I want to as well. And rewrite this in terms of u. So my volume now is going to be pi times, or actually negative, I'm going to bring out the negative, all right, times the integral of root u, because again, u is being rooted, all right, du. Okay, now the root of u, and I'm not going to put the bounds in here from 0 to 4, because those are bounds, those original bounds are in terms of x. X equals 0 to x equals 4, those are in terms of x. If I want to put my bounds in now, I'd have to use my my substitution here to get that. Originally, when x equals 0 here, u should be 16 minus 0 squared, or 16. So I can put a 16 there if I want. And when x equals 4, well, 16 minus 4 squared is 0, so I can put a 0 here if I want. These are in terms of u. So equals u here. New bounds, because I have an integral now in terms of u. Well, now I want to integrate. So I get negative pi times the integral of u to the 1/2, and that's going to be u to the 3/2, all right, divided by 3/2, evaluated from 16 to 0. Or I could bring back x in and evaluate it at the original bounds from 0 to 4. You can try that. It's going to give you the same thing. Okay, I'm going to simplify this a little bit here. Negative pi times 2/3, all right, times u to the 3/2. Evaluate that from 16 to 0. There you go. Okay, so what is that? Let's finish that. So I've got negative 2 pi thirds. Okay, evaluate the function at 0 first, so that's 0 to the 3 halves minus 16 to the 3 halves. Evaluate the function and just keep the constant out and just evaluate the function, the variable, at these upper and lower bounds, or upper and lower limits. That's the easiest way to handle it. So you get negative 2 thirds pi times negative something. That's a 0 minus something. It's negative. The square root of 16 is 4. 4 cubed is 64.
Okay, Cactus.
Sorry about that. 4 cubed is 64. Negative 7 is a negative is a positive, so you get 128 pi thirds cubic units, and that's your volume. So regardless of whether you use the shell method or the disk method, you're going to get the same result. And again, check with the TI-84 and go function integration. All right, enter the function in, enter your variable in, enter the left and or upper and lower bounds, and check with a decimal. Okay, just remember that. Okay, next problem on the other side deals with setting up and evaluating an integral to find the solve of revolution about the x-axis now. Do this two ways, using washer method and then shell method, and then change the cross-section in the shell method. Okay, washer method first. Okay, we're going to revolve around the x-axis this way here. So the first thing I'm going to do is just sketch this and reflect it over here and sketch it below the axis so I can draw this in 3 dimensions. First, note that this is the cubic function, this is the squared function. You guys should know that. The parabola is in red here. Okay, and the cubic is in blue. Right there, x cubed. Okay, so what we need to do is go ahead and reflect this across here. 1, 1, they intersect here at 1, 1. So come down here 1 unit. Let's say this is at negative 1. So they intersect right here. And I'm going to just do a really rough sketch here. Okay, there's the same region below. So all of this area in blue is reflected to yellow, and it gets revolved around the x-axis. So let's talk cross-section here. This is set up for the disk method, or excuse me, washer method. Okay, this is one washer right here. Okay, why is it a washer and not a disk? Well, it's because it's got a hole in it. So what you need to do is figure out the inside radius. Sorry about all the interruptions. I can't stand that. I got to figure out the inner radius and the outer radius. And this is big R and little r here. Okay, the outside radius first. Okay, outer radius. Outer radius, notice that the height here is given by the parabola in red here, so x squared. Okay, so it's going to be a y value which is equal to the parabola x squared. The inner radius is here on the cubic function, and so little r is going to be the inner radius, which is equal to a y value. It's vertical now, but what is that equal to on the blue function? Well, it's equal to x cubed. Okay, and what we want to do is figure out a typical washer volume. Okay, well, that's equal to pi times big R squared minus little r squared times the thickness, which in this case is dx, because it's vertical cross-section here. So let's simplify this before we integrate. So we're going to have pi times big R squared, which is x squared squared minus little r squared, which is x cubed squared times the thickness. You, of course, want to simplify this to x to the 4th minus x to the 6th. You've got to multiply the exponents there times your thickness. And that's a typical washer volume. Now, the washers are built from left to right, from 0 to 1. So you look for your bounds this way. Why is that again? Well, again, you can draw your cross-section anywhere you want. I mean, I could have drawn it right here. Okay? So starting at 0 all the way to 1 from left to right are how the washers are being built, or how the cross-sections are being made. So bounds are found laterally or horizontally from 0 to 1. So my volume is now the integral from 0 to 1 of my washer volume pi times x to the 4th minus x to the 6th dx. So the question is, what is that? When you integrate, it's pi times x to the 5th divided by 5 minus x to the 7th divided by 7, evaluated from 0 to 1. So we're going to get pi times, 1 to the 5th is 1 divided by 5 is 1/5 minus 1/7. Okay, minus pi times 0. What is that? Well, it's pi times 7 minus 5 divided by 35. And that's going to be equal to 2 pi 35ths. All right, cubic units. There's my volume. That's using a washer method where the cross sections are vertical. If you make cross sections horizontal, you don't have a washer, you have what's called a shell. So let me show that in the second example here. Okay, now we're going to have to redraw the cross sections. Okay, so what first I'm going to do is I'm going to reflect over here and draw the curves again. Draw the bounded region basically. And I have this region in blue here. It gets reflected on the yellow region here. And again, we're revolving around the x-axis. But this time we want to use shells. Shell method. Okay, so to do that, what we do is we change the cross section. We want to go here. There's my cross section. Here's the cross section reflected. And let me draw it in 3 dimensions. Here's your shell. Okay, now that looks different than my previous one above. Okay, and what we need to do is figure out the radius of the shell, which is this distance here, that's r. Notice the radius is vertical. Alright, and then I also need to figure out the height, which is this distance right here, h. And that's horizontal. Now let's talk about the height for a moment. The height, since it's horizontal distance is always found by taking right minus left. Okay, so I need this point minus this point. So this point is on the cubic, so it's going to be cubic minus parabola from right minus left. Okay, so, but there are x values here. What is the x value here? And what is the x value here? I don't know. I got to solve for x in both of these. It's going to be, x2 minus x1, whatever that is, but I got to solve for x in both of these. I got to solve for x. Okay. Also notice here that the thickness here is dy. And any thickness involves, when the thickness is dy, you have to write an integral in terms of y, which means you got to take both functions and solve for x in terms of y. So for y equals x squared, you square root both sides and you get square root of y equals x. When y is equal to x cubed, you cube root both sides, so the cube root of y equals x. So you got to solve for x. So it's going to be cubic minus parabola, but in terms of y and not in terms of x. So in this case, it's going to be the cube root of y minus the square root of y for your height. Because you're on the cubic polynomial here on the right side, minus the left side to get the horizontal distance or the height of the shell. Okay, what's the radius? Well, it's some y value, it's some height. Remember, when the radius is vertical, just let it be y. So the radius is just y in this case. So the shell volume is going to be 2 pi r, which is y, times the height now, which is the cube root of y minus the square root of y times the thickness dy. That's one shell volume. And what you want to do is integrate that to get the total volume. The question is, what are the bounds of integration? The horizontal cross sections start at 0 and they get built up all the way up to 1. So the bounds are found by looking vertically, where a is equal to 0 and b equals 1. They intersect here at 1. So we're going to integrate from 0 to 1 of the circumference, which is 2 pi y, times the height, which is the cube root of y minus the square root of y times the thickness dy. And before we do that, what we want to do is distribute through the y and pull out the 2 pi. This can go outside the integral, and you want to take this and distribute it twice in. Keep in mind that cube root of y is 1/3 power, and the square root of y is a 1/2 power. So what I have here is the integral from 0 to 1, or actually 2 pi times that, times y to the 1/3 minus y to the 1/2 dy. Well, what's that? Well, it's 2 pi times the integral from 0 to 1 of y to the 4/3, because you've got to add the exponents when you distribute through. 1 plus 1/3 is 4/3. 1 plus 1/2 is 3/2, so you get y to 3/2 here, dy. You integrate, and you get 2 pi times, let me see, 4/3 plus 1 is 4/3 plus 3/3, or 7/3, so you get y to the 7/3 here. You've got to divide by 7/3, which is the same thing as multiplying by 3/7. Okay? Minus, okay, y to the 3/2 plus 1, so y to 3/2 plus 1 is 3/2 plus 2/2 is 5/2, divided by 5/2, which is the same thing as multiplied by 2/5. Evaluated from 0 to 1. Okay, and what do you have? Well, you have 2 pi times 3/7 minus 2/5, because you just substitute 1 in there, and that's what you get. When you substitute 0 in there, you get 0, so it's going to be 2 pi minus, or times 0. When you simplify this, you get 2 pi times 15 minus 14, all divided by 35, and that's 2 pi divided by 35 cubic units for your overall volume. That's how you use your shell method. Again, you're going to check with the calculator, check with TI-84, okay, using the function integration, FN and then INT, function integration mode, and verify the results. Okay? If you need some more help, see me in class, and study hard, do the right thing, practice. That's how you get good, is by pure practice. Do these problems 2 or 3 times each, and do them as easily as me, and then you're going to be much better in class. I'll see you then.